A topic we know and love, induction, of course. So here's one with an inequality. Now, one of the misconceptions is, of course, that inequalities are only in extension 2, but of course they could appear in extension 1 as well. They do more often appear in extension 2 than extension 1. So we're going to prove this little one. Now, by the way I'm about to set this out, no, you can't do it before you ask. Okay, I'm just going to do it a quick way so we can move through these a lot quicker. So test n equals 1. Left-hand side is 1. Right-hand side is 1. Very good. Left-hand side is less than or equal to the right-hand side. In this case, it's equal to. My assumption, this is the bit I'm saying, no, you can't do this, okay? But I'm just writing down my assumption, n equals k would end up being that. And what I want to prove is that. Okay, let's do our proof. It's a series type, so I will rewrite it as sum to n terms plus the nth plus 1th term. Our assumption was 1 plus all the way up to 1 on k squared is less than or equal to 2 minus 1 on k. Now we're trying to show this whole thing is less than 2 minus 1 on k plus 1. So I'm not going to touch the 2 minus, because that's part of what I want to prove already. So it's got to be the algebraic fraction that I'm going to have to manipulate somehow to be 1 on k plus 1. So I'll make it all one fraction. Notice the next line now says equals. It doesn't say less than or equal to, because this line is actually equal to that line. It's not less than that line. No. So the algebraic fraction, and of course be careful with the negative on the k there. That's a common mistake to be made, that people carry through the plus. But if I'm making the whole fraction negative, the negative will become the positive. So we've got k plus 1 squared minus k on the top, k squared plus k plus 1. Now, that's close to what I want. Remember, we're trying to get just 1 on k plus 1. So ideally, if the top was k outside of k plus 1, it would cancel and it would work nicely. But I haven't quite got that. So I'm going to just write what I want. I want k squared plus k. But then I've still got this annoying minus 1 on k plus 1 squared there. But that's not a big deal, because I'm not dealing with an equality, I'm dealing with an inequality. So k is a positive number, remember? So 1 over k plus 1 all squared must be positive. So I'm saying I'm subtracting something positive. Well, if I'm subtracting something positive, it must be less than. So look at what this closely. I'm saying this top line is less than the bottom line. Now I can say that because the line above it is the same thing but minus something positive. So therefore it's got to be less than. Because if I've got something, I don't know, let's say I've got 20. But if I subtract something positive from it, it's got to be smaller. Okay? So be careful how you read it, because some people read it the wrong way. We're saying this top line is less than the next line. Right? Which must be true, because the line above says minus 1 on k plus 1. And then that's what we want. The k plus 1 cancels, and I get 2 minus 1 on k plus 1. And so therefore we've got our result, hence, etc., etc., etc. Let's have a look at something a little bit different. So these are the ones where we set up a recurrence relation. So it's like a series, but rather than writing the series out, we just say how we create the next term and so on. So my first term is the square root of 2, and then to create every term after that, it's going to be the square root of 2 plus the term we just did. We're going to show that every single term will be less than 2 in this particular series. So it's not an arithmetic series or a geometric series, it's just a pattern. All right, let's have a look at the first one. First one, well, they've told me the first term is the square root of 2, and square root of 2 certainly is less than 2. There's no question about that. My assumption will be that the general term there is less than 2. I want to prove that the next term is also less than 2. Okay. Well, all I've got to work with is the formula they've given me. And I know that the term k plus 1 will be the square root of 2 plus term k. But I've assumed that term k is less than 2. So therefore, term k plus 1 must be less than the square root of 2 plus 2. Well, 2 plus 2 is 4, and the square root of 4 is 2. Therefore, every term is less than 2. Let's have a much more fun one then. This series is actually, there's two number patterns going on, but they're linked each term. So in the x number pattern, to get a particular number, we get the one before in the x pattern and the one before in the y pattern, add them together, or average them, if you like. To get the next number in the y pattern, we multiply the two and divide by what they add together to give. We're going to prove whenever we get a number from the x pattern and the equivalent number in the series from the y pattern, multiply them together, we'll always get the number 10. That's what we're going to prove. Well, n equals 1, I think, well, we can see it. They've told us the first term is 5, and then, sorry, not the second term, but the first term in the other pattern is 2. 5 2s are 10. So it certainly works when we grab the first term of each pattern. So we're going to assume that when we get the kth one of each pattern, they multiply together to give 10. We now want to prove that if we get the k plus 1th of each pattern, we'll also get 10. Okay. Well, I've substituted in the general formula that they gave us, and you'll notice it actually works out very quickly. What looks like a horrible... You don't notice that? Well, it is. So what initially looks like something terrible actually is very, very easy, because the numerator cancels with the denominator, and oh look, it equals x, which we know is 10. There it is. So sometimes they can look absolutely horrible, but they actually fall out very quickly. So yeah. All right, let's play with Fibonacci numbers. That's so much more fun. Okay. Remember, a Fibonacci sequence is when, to get a particular number in the pattern, you add the two previous numbers. The classic Fibonacci sequence is the one that starts with 1, 1, so that both the first and the second term is equal to 1. We're now going to prove that every term in the Fibonacci sequence is less than, and I know you're as excited as me when you see this number, 1 plus the square root of 5 on 2 to the power of n. And the significance of 1 plus the square root of 5 on 2 is, of course, the golden ratio. It's a wonderful result. Let's prove it true for n equals 1 and n equals 2. Why both? Good question. Because when I do my proof, I'm going to end up using the formula. And you'll notice there's actually two terms I need to substitute in the formula, the nth term and the nth minus 1. So I'm going to have to make two assumptions to be able to substitute in. So left-hand side's equal to 1 for the first term. Second term's also 1, of course. But we're trying to prove it's less than the golden ratio to the power of 1. Well, as I say, it was 1.6180 something, but 1.62. It's certainly less than 2 anyway. So yes, the first term works. Second term, we're now going to square the golden ratio, and we get 2.62. Yes, 1's less than that as well. So it does work for the first two terms. So I'm going to have to make two assumptions now. One for term k minus 1, one for term k, which we're going to prove the k plus 1th term. Okay, here we go. So I'm going to start with the relationship they gave me. That way I can substitute in my assumption. I know this is going to be less than 1 plus root 5 on 2 to the power of k plus to the power of k minus 1. We're trying to show it's less than 1 plus root 5 to the power of k plus 1. Well, the logical thing to do then is factorise. However, I haven't done the logical factorisation. Normally when you factorise, you would take out the lowest power. I haven't bothered doing that. I know I want to prove it's 1 plus root 5 on 2 to the power of k plus 1. That's what I've factorised out. Because then what's left in the parentheses, all I've got to do is show that's less than 1. If I can show that's less than 1, then the whole thing is less than 1 plus root 5 on 2 to the power of k plus 1. So that's why I took out a power of k plus 1 rather than how we would normally factorise. So what's left in there? 1 plus root 5 on 2 to the power of minus 1, and also to the power of minus 2. Okay. So turn it upside down because it's the power of minus 1. The other one will become 1 plus root 5 squared. look what happens. When you expand out 1 plus root 5 all squared, you get 6 plus 2 root 5. So actually, that's equal to 1. There's our result. Woo, what? Right? So, power minus 1, turn it upside down, that's 2 on 1 plus root 5. Power minus 2, turn upside down, so we get 4 on 1 plus root 5 squared. So the common denominator is 1 plus root 5 squared, which means the first fraction, the numerator becomes 2 plus 2 root 5, which is 6 plus 2 root 5, which also happens to be 1 plus root 5 all squared. And so that's equal to 1. So yes, that one works. But as mentioned, in your conclusion for this one, your conclusion would be slightly different because you've made two assumptions. You would say, well, since it's true, hence it's true for k plus 1, if it's true for k and k minus 1, and then you say, well, since it's true for 1 and 2, then it's true. Okay. 10E in our Patel has a few induction questions. I think I threw a sheet in there as well, which has some different ones. We got the past HSCs, all the different papers as well to look at for examples.